Hydrocarbons are organic compounds containing only hydrogen and carbon. They play an important role in our life as they meet more than 90% of the energy requirements of the world. Also, they are the major sources of various other organic compounds which we use in different walks of life. Coal and petroleum are complex mixtures of hydrocarbons. Coal tar, a product of destructive distillation of coal, when subjected to fractional distillation, produces various aromatic compounds including benzene. These compounds are used in the preparation of various industrially useful products such as polymers like polystyrene, dyes, drugs, etc. Petroleum, on the other hand, is a major source of alkanes and cycloalkanes. When it is subjected to fractional distillation, the various fractions obtained are used as fuels for different purposes. For example, natural gas in the form of CNG, that is, compressed natural gas, and LNG, that is liquefied natural gas, are used as automobile fuels. Liquefaction of petroleum gas renders a very useful domestic fuel in the form of LPG. Kerosene oil is also used as a domestic fuel, but it is more polluting as compared to LPG. Petrol and diesel are also used as automobile fuels. Among the automobile fuels used, CNG or LNG are the clean fuels. That is, these are non-polluting fuels. Other higher hydrocarbons are used as lubricants, solvents for paints, and so on. Hence, we can say that the hydrocarbons act as sources of energy. Now, let us look at the classification of hydrocarbons. On the basis of carbon skeleton, that is, the type of carbon-carbon bonds, hydrocarbons can be classified into three main categories: saturated, unsaturated, and aromatic hydrocarbons. Saturated hydrocarbons are the hydrocarbons consisting of carbon-to-carbon single bonds. Saturated, open-chain or acyclic hydrocarbons in which carbon atoms are linked by straight or branched chains are called alkanes. The general formula for alkanes is CnH2n plus 2. where N is equal to the number of carbon atoms present. For example, propane. Saturated hydrocarbons in which the carbon atoms join together to form a closed chain are called cycloalkanes. The general formula for cycloalkanes is CnH2n, where N is equal to the number of carbon atoms present. For example, cyclopropane. Unsaturated hydrocarbons consist of one or more carbon-to-carbon multiple bonds. That is, a double bond or a triple bond or both. Unsaturated, open chain or acyclic hydrocarbons in which carbon atoms are linked by straight or branched chains containing at least one carbon-to-carbon double bond are called alkenes. The general formula for alkenes is CnH2n, where N is equal to the number of carbon atoms present. For example, propene. Unsaturated, open chain or acyclic hydrocarbons in which carbon atoms are linked by straight or branched chains containing at least one carbon-to-carbon triple bond are called alkynes. The general formula for alkynes is CnH2n-2, where N is the number of carbon atoms. For example, propyne. Aromatic hydrocarbons are cyclic hydrocarbons with alternative double bonds in conjugation. Aromatic compounds are benzene and the compounds that resemble benzene in their chemical behavior. For example, benzene, toluene, etc. As we learnt, alkanes are the simplest form of hydrocarbons containing carbon-carbon single bonds. Its molecules consist of carbon-hydrogen bonds and carbon-carbon single bonds. Since each carbon is bonded to 4 other atoms through single covalent bonds, the compounds are called saturated compounds. They contain carbon-carbon single covalent bonds which are strong sigma bonds. Due to this, the compounds are almost chemically non-reactive at normal temperature and pressure. This is why they were earlier known as paraffin, which, in Latin, means little affinity. We have learnt that the general formula for alkanes is CnH2n+2, where N stands for the number of carbon atoms and 2n+2 stands for the number of hydrogen atoms in a molecule. The most simplest alkane is methane. It has one carbon atom connected to 4 hydrogen atoms. The next member, ethane, can be obtained by replacing one of the hydrogen atom of methane by the CH3 group. This group is methyl group, which is a type of alkyl group. Thus, ethane with molecular formula C2H6 is derived by replacing one hydrogen atom by CH3 group from the methane CH4 molecule. Similarly, an entire series can be obtained by replacing one hydrogen with the CH3 group. There is no limit to the number of carbon atoms that can be linked together. However, as the number of carbon atoms within a molecule goes on increasing, the structure becomes more and more complex. When a carbon atom is attached to hydrogen or just one other carbon atom, it is said to be primary carbon. When a carbon atom is attached to 2 other carbon atoms, it is said to be secondary carbon. When a carbon atom is attached to 3 carbon atoms, it is said to be tertiary carbon. And when all the bonds formed by a carbon atom are with 4 other carbon atoms, it is said to be neo or quaternary carbon. In a molecule, the terminal carbon of a carbon-carbon chain is always attached to 1 carbon and 3 hydrogen atoms, and hence it is called primary carbon atom. The first 3 alkanes in the series, methane, ethane and propane, only have one molecular structure. However, as the number of carbon atoms in an alkane goes on increasing, we get more than one structural arrangement for a particular molecular formula. Such compounds are called isomers. The phenomenon of exhibiting isomers is called isomerism. For example, in butane, we get 2 possible structures, one as a continuous chain and the other branched. Now, Although the chemical formula for all these structures is the same, their properties differ due to the differences in their carbon chain structure. Such compounds are called chain isomers. In pentane, we get three possible structures. 1. A continuous chain with secondary carbon atoms. Another with one tertiary carbon atom, and the third with neo or quaternary carbon atoms. Here, the structural isomers differ in the carbon chain structure and hence are called chain isomers. The table here gives the number of isomers present for a given molecular formula. Butane has 2 isomers and pentane has 3. Similarly, as the number of carbon atoms goes on increasing, the number of structural isomers goes on increasing. We come across many groups like CH3, C2H5 attached to carbon atoms. These groups are derived by removing one hydrogen atom from alkanes and are known as alkyl groups. Their general formula is CnH2n plus 1. The name of the alkyl group is derived from name of the parent alkane by replacing suffix ane of alkane with yl. We have learnt that the properties of a compound depend upon the structure of the compound. However, these compounds have the same molecular formula. So, how do we differentiate between them and how do we decide their names? To address the issue, the International Union of Pure and Applied Chemistry, or IUPAC, has come up with standard rules for naming compounds. The key steps to label a structure are: identify the longest continuous chain of carbon atoms. Name this longest parent carbon chain using standard naming rules. Add the name of each side chain before the name of the parent carbon chain. Number the parent carbon chain so that the sum of the members assigned to each substituent will be a least number. Write the name of the side chain with its number before as prefix to the name of the root word of the parent carbon chain. If there are multiple side chains of the same type attached to the parent carbon chain, use prefixes such as di and tri to indicate it with its assigned number to the parent chain. Let's again look at the 3 structures that we had obtained for pentane, C5H12, and label them as structure 1, 2, and 3. Now, first identify the longest continuous chain of carbon atoms. Structure 1 contains 5 carbon atoms. Structure 2 contains 4 carbon atoms. And structure 3 contains 3 carbon atoms in the parent carbon chain. Next, name this longest parent carbon chain using standard naming rules. This name for structure 1 is pentane, structure 2 is butane, and structure 3 is propane. Since structure 1 doesn't have any branches, its name is pentane. Now, in structure 2 and 3, add the name of each side chain before the name of the root chain. So, in structure 2, we add methyl before butane, and in structure 3, we add methyl before propane. Now, number the parent carbon chains so that the sum of the numbers assigned to each side group will be least. In structure 2, the carbon atoms are numbered 1 to 4 with the substituent alkyl group at carbon atom number 2. In structure 3, the carbon atoms are numbered 1 to 3 with both the substituent alkyl groups attach to carbon atom number 2. Then, number and name the side chains and write as prefix to the name of the parent carbon chain. With this, we have named structure number 2 as 2-methylbutane. However, structure 3 has multiple side chains of the same type of carbon atom number 2. So, we take the 6th step, which is to use prefixes such as di and tri to indicate the groups and number each one in the name. Thus, the name of the third compound is 2,2-dimethylpropane. With this, we have labeled all the 3 structures. Just like it's important that we know how to write correct IUPAC names for a compound given its structure, we also need to be able to draw the structure given its IUPAC name. The key steps to draw a structure from a given name are: draw the chain of carbon atoms from the molecular formula. Number the carbon atoms within the parent carbon chain. Attach the substituent alkyl groups given as prefix in the name to the carbon atoms as specified in the numbering. Satisfy the remaining valence of each carbon atom by putting the requisite number of hydrogen atoms. Let us now try and draw the structure of 3-ethyl-2,2-dimethylpentane. First, from the base name, pentane, we can deduce that the parent carbon chain contains 5 carbon atoms. Second, number these carbon atoms. Third, from the name we can identify that we have to attach an ethyl group to atom number 3 and 2-methyl group to atom number 2. Fourth, fill in the remaining places with hydrogen atoms such that each carbon atom fulfills its valence of 4. Alkanes can be obtained in a laboratory either from unsaturated hydrocarbons, alkyl halides, or carboxylic acids. Let's look at each one in detail. Unsaturated hydrocarbons, like alkenes, react with hydrogen in the presence of finely divided catalysts like platinum, palladium, or nickel to form alkanes. As this reaction involves addition of hydrogen, it is called hydrogenation. The surface of these metals absorb hydrogen gas and activate the hydrogen-hydrogen bond. The reaction using platinum and palladium can be catalyzed at room temperature. However, the reaction using nickel as a catalyst requires relatively higher temperature and pressure. For example, ethane on hydrogenation in presence of catalysts such as finely divided platinum, palladium, or nickel gives ethane. To obtain alkanes from alkyl halides, we can either use the reduction method or the Wurtz reaction. Alkyl halides on reduction with reducing agents such as zinc-copper couple in ethanol or zinc and dilute HCl gives alkanes. For example, ethyl iodide, when reduced by using zinc-copper couple in ethanol or zinc and dilute HCl, gives ethane. Now let's see how to obtain alkane from alkyl halides using the Wurtz reaction. Alkyl halides on treatment with metallic sodium in presence of dry ether give higher alkanes with even number of carbon atoms. This reaction is known as Wurtz reaction. For example, the reaction of bromomethane with sodium metal in presence of dry ether gives ethane. It is important to note that when two different alkyl halides are taken, then a mixture of alkanes is produced. For example, the Wurtz reaction of mixture of methyl iodide and ethyl iodide forms ethane, butane, and propane respectively. As alkanes have close boiling points, it becomes very difficult to separate them from the mixture. Hence, this method is not suitable to prepare the alkanes with odd number of carbon atoms. Now, let's see how alkanes can be prepared from carboxylic acids. Sodium salts of carboxylic acids on heating with soda lime give alkanes with one carbon atom less than the parent carboxylic acid. Soda lime is a mixture of calcium oxide and sodium hydroxide. As this reaction involves the elimination of carbon dioxide from a carboxylic acid molecule, the process is known as decarboxylation. For example, sodium propionate on heating with soda lime gives ethane. Coal-based electrolytic method is yet another method to prepare alkanes from carboxylic acids. This method involves the preparation of alkanes with even number of carbon atoms through the electrolysis of aqueous solutions of sodium or potassium salts of carboxylic acids. For example, the aqueous solution of sodium or potassium acetate on electrolysis gives ethane. The mechanism of the reaction can be understood through the following steps. At anode, the acetate ions in the solution lose electrons at the anode and form acetate free radicals. The acetate free radical lose carbon dioxide molecule and thus form methyl free radicals. The methyl free radicals further react and form ethane gas. At cathode, water molecules accept the electrons and split up into hydroxyl ions and hydrogen free radicals. Two such hydrogen free radicals combine together and form hydrogen gas. Thus, in coal-based electrolysis method, alkane is produced at the anode. First, let's look at the physical properties. These include appearance, color, odor, boiling point, solubility, and polarity, among others. These properties depend on the attractive forces working on the molecules. As we have learned, alkanes consist of only carbon-to-carbon and carbon-to-hydrogen single bonds. These bonds are covalent, and the electronegativity between two carbon atoms or between carbon and hydrogen is almost negligible. Hence, the molecules formed are non-polar. This is why the only attractive force acting on these molecules is the weak van der Waals forces. Therefore, the first four members of the series, C1 to C4, are gases. C5 to C17 are liquids, while the molecules containing 18 or more than 18 carbon atoms are solids at 25 degrees Celsius. They are all colorless and odorless. Due to their non-polar nature, these compounds are insoluble in polar solvents like water and soluble in non-polar solvents like benzene. Their boiling point is decided by the strength of the van der Waals force. This force is very sensitive to distance. Hence, for a strong force of attraction, the molecules need to be held close together. However, in alkanes, because of their nonpolar molecules, the van der Waals forces are weak, and hence their boiling points are much lower than expected. As the size of a molecule increases, its surface area increases. Thus, the strength of the intermolecular van der Waals force also increases. A linear or straight chain alkanes like pentane has a higher boiling point than its branched isomers like 2-methylbutane and 2,2-dimethylpropane. This is because branching reduces the surface area of a molecule, leading to a weakening of the van der Waals forces, which are then overcome at relatively lower temperatures. Now, let's look at the chemical properties of alkanes. As we have seen, alkanes are nonpolar. Their carbon bonds are quite stable, and so they do not easily react with acids and bases. However, they do undergo substitution reactions and combustion reactions under certain conditions, as their carbon atoms are in strongly reduced states. During this reaction, the hydrogen atom of an alkane is substituted, and hence the reactions are called substitution reactions. When the element substituting the hydrogen is a halogen, the reaction is called halogenation. It involves 3 steps: initiation, propagation, and termination. Let's go through each step by observing the chlorination of methane. During chlorination of methane, the 4 hydrogen atoms of methane are step by step substituted or replaced by chlorine atoms, forming tetrachloromethane as the final product. During initiation, the chlorine molecule is homolyzed in the presence of heat or light, forming chlorine-free radicals. During propagation, 2 reactions take place. First, the chlorine-free radical attacks the methane molecule, forming a methyl-free radical and hydrogen chloride. Next, the methyl-free radical attacks the second chlorine molecule, forming chloromethane, and one more chlorine-free radical, setting up the chain reaction. The chlorine-free radical formed sets up many other propagation steps to form more halogenated products. These steps are repeated till all the hydrogen atoms in the methane molecule are replaced by chlorine atoms. During termination, the reaction stops either because all the reactants have been consumed or because of the following possible chain terminating reactions. One possible reaction is that 2 chlorine-free radicals combine to form a chlorine molecule. Another possible reaction is that 2 methyl-free radicals combine to form ethane. Or a chlorine-free radical and a methyl-free radical combine to form chloromethane. Thus, in the chlorination of methane, ethane is obtained as a byproduct. Now let's understand the combustion reaction of alkanes. On heating, alkanes get completely oxidized to carbon dioxide and water along with heat. In the presence of air or dioxygen. This is why alkanes are used as fuels. When alkanes undergo incomplete combustion, they form carbon black. It is used in the manufacturing of ink, printer ink, black pigments, and as filters. Alkanes, like methane, on heating at high pressure with a regulated supply of oxygen and in the presence of a suitable catalyst, provides a variety of products like methanol and methanal. Ethane gives ethanoic acid, and an alkane with tertiary hydrogen atom like 2-methylpropane gives corresponding alcohol. When a normal alkane like N-hexane is heated in the presence of anhydrous aluminium chloride and hydrogen chloride gas, it isomerizes to a branched chain alkane like 2-methylpentane and 3-methylpentane. Alkanes undergo aromatization or reforming. That is, a normal alkane with 6 or more than 6 carbon atoms like N-hexane, when heated to 773 Kelvin at 10 to 20 atmospheric pressure in the presence of a catalyst like oxides of vanadium, molybdenum or chromium supported over alumina, gets dehydrogenated to form cyclic compounds like benzene or its homologues. Alkanes also react with steam. This reaction is used in the industrial preparation of dihydrogen gas. For this, methane is heated at 1000 degrees Celsius in the presence of nickel, along with steam to form carbon monoxide and dihydrogen gas. Higher alkanes at higher temperatures decompose to form lower alkanes and alkenes, amongst others. This reaction is also known as pyrolysis, or alkanes with 2 or more carbon atoms like ethane and propane consist of carbon-to-carbon single covalent sigma bonds, in which the electrons are shared symmetrically around the internuclear axis of the carbon-carbon single bonds. The atoms within a molecule are in constant rotational movements along the internuclear axis, as the molecular orbitals are not disturbed due to rotation. Due to this, the shape of an alkane molecule can be twisted into different three-dimensional arrangements by rotation about the carbon-to-carbon single bond or bonds. These different three-dimensional arrangements are interchangeable and are called conformations. These interconversions are very rapid, and hence, in a short span of time, a given molecule may exist in infinite different conformations. However, remember, conformations do not affect the bond angle and the bond length. Now let's understand the concept of conformation better by using the ethane molecule as an example. We can see that each carbon atom is attached to 1 carbon and 3 hydrogen atoms. Now, imagine one of the carbon atoms along with its hydrogen bonds rotating around the internuclear axis of the carbon-to-carbon bond. You can see that this rotation causes infinite different spatial arrangements of the hydrogen atoms of 1 carbon atom with respect to the hydrogen atoms of another carbon atom. These arrangements are called conformational isomers. In reality, both the carbon atoms will be going through such rotations, thus increasing the number of spatial arrangements. Let's study these in detail. We can observe that there are 2 extreme positions of the hydrogen bonds of 1 carbon in relation to the hydrogen bonds of another carbon atom. 1. where the hydrogen atoms attached to the two carbon atoms are as close as possible to each other, and the other where they are as far apart as possible. When the arrangement has the hydrogen atoms close to each other, the three hydrogen atoms and carbon atoms at the back are hidden by the three hydrogen atoms attached to the carbon atom in the front. And so the arrangement is known as eclipsed conformation. The arrangement wherein the hydrogen atoms are far from each other, the three hydrogen atoms and carbon atoms at the back are visible behind the three hydrogen atoms attached to the carbon atom in the front, giving the arrangement a neatly distributed look. And so the arrangement is known as staggered conformation. All the arrangements between the eclipsed and staggered positions are known as skew conformations. In the eclipsed conformation, the molecule is the least stable as the repulsive force between the electrons is the maximum. This is due to close spatial arrangement of the carbon-hydrogen bonds. In the staggered conformation, the molecule is the most stable, as there is minimum repulsive force between the electrons. This is because the carbon-hydrogen electrons are the farthest from each other. The repulsive interaction between the electron clouds in a molecule, which affects the stability of a conformation, is called torsional strain. Its magnitude depends upon the angle of rotation about the carbon-to-carbon bond. This angle is known as torsional or dihedral angle. The energy difference between eclipsed and staggered conformations is 12.5 kilojoules per mole, which is easily overcome at room temperature and pressure. Due to this, it is not possible to separate different conformation isomers of ethane. Now that we have seen what conformation means, let's learn the two standard visual representations used to explain it. These are known as sawhorse projection and Newman projection. In sawhorse projection, the molecules are viewed along their molecular axis, that is, at an oblique angle. Here, the carbon-to-carbon bond is shown as a long straight line, whose upper end is bent slightly either towards the left or towards the right-hand side. The front carbon is shown at the lower end of the line, and the back carbon at the upper end. Each carbon has 3 hydrogen atoms attached to it. These bonds are shown with the help of 3 lines attached to the carbon atom. These are inclined at an angle of 120 degrees to each other. Using sawhorse projection, the 3-dimensional structure of the eclipsed and staggered conformations can be easily visualized. In Newman projection, the carbon-to-carbon bond conformation is viewed head-on, that is, front to back. The carbon atom at the front is represented as a dot, and the carbon atom at the back is represented as a circle. The hydrogen atoms attached to the carbon atoms are shown by lines. The bond angle between these lines is kept at 120 degrees. The hydrogen atoms connected to the carbon atom in the front are represented by longer lines, and those connected to the carbon atom at the back are represented by shorter lines. Using Newman projection, an unsaturated hydrocarbon with a double bond in between the carbon atoms is called an alkene. Alkenes are also called olefins, which means oil forming, as its first member, ethene, on reacting with chlorine, forms an oily substance. As you have studied, a carbon-to-carbon double bond consists of one strong sigma bond and one weak pi bond. A sigma bond is formed due to the head-on overlap between two sp2 hybrid orbitals of two carbon atoms, whereas a pi bond is formed due to the sideways overlap between two pure 2p orbitals of two carbon atoms. Due to the presence of a double bond, an alkene has two hydrogen atoms less than corresponding alkane. Hence, the general molecular formulae of alkenes is CnH2n. The pi bond, which consists of loosely held delocalized pi electrons, serve as a source of electrons for the electron-seeking reagents. Thus, the electron-seeking or electron-deficient reagents, called electrophilic reagents, attack weaker pi bond in alkenes and form corresponding saturated compounds. The presence of the weaker pi bond makes alkenes more reactive than the corresponding alkanes. The IUPAC name of the alkenes can be divided into two parts, that is, root word, which indicates the length of the carbon chain, and suffix -ene, which indicates the double bond. For example, the IUPAC name of an alkene with two carbon atoms can be divided into two parts, that is, root word eth plus the suffix -ene. Hence, the IUPAC name is ethene. In the IUPAC system, alkenes are named by replacing the suffix -ane of the corresponding alkanes by the suffix -ene. For example, ethane is named from ethane by replacing the suffix -ane with -ene. For alkanes with more than 3 carbon atoms, the carbon with a double bond is given the least number, and the number is indicated in the name. For example, but1-ene, but2-ene. An alkane with an alkyl group as a substituent is numbered in such a way that carbon with double bond gets least number. While naming, the number of the carbon atom with the substituent and the name of the substituent, that is alkyl group, is written as a prefix to the name of the parent carbon chain. For example, the following molecules are named as 2-methyl-prop-1-ene, 3-methyl-but-1-ene respectively. In higher alkenes, molecules can be arranged in more than one way. For example, the molecule of alkene with 4 carbon atoms, that is C4H8, can either be arranged as but1-ene, but2-ene, or 2-methyl-prop-1-ene. These are called structural isomers. In addition to this, it is observed that C4H8 shows 2 distinct special arrangements. They are cis-2-butene and trans-2-butene. These are called stereoisomers. Thus, higher alkenes are said to show both structural and stereoisomerism. In structural isomerism, they show chain and position isomerism. In stereoisomerism, They show geometrical or cis-trans isomerism. In a molecule of C4H8, all the carbon atoms are present in the form of straight or branched chains. For example, structures 1 and 2 have straight chains, whereas structure 3 has a branched chain. Structures 1 and 3 and 2 and 3 are said to be chain isomers of each other. When in two structures, the position of the double bond alone is different, they are said to be position isomers. Structures 1 and 2 are position isomers. A compound like but2-ene shows two distinct configurations or spatial arrangements, and hence, its molecules are said to show geometrical isomerism, a type of stereoisomerism. When the two CH3 groups attached to each carbon atom of the double bond are on the same side, the isomer is called a cis isomer. On the other hand, when the two CH3 groups attached to each carbon atom of the double bond are on the opposite side, the isomer is called as trans isomer. Due to the difference in the spatial arrangement, cis and trans isomers have different melting points, boiling points, dipole movement, solubility, and many other properties. For example, the cis but2-ene molecule is polar, whereas the trans but2-ene molecule is non-polar. This is because in a cis but2-ene molecule, as the two CH3 groups are on the same side of the double bond, there is a greater, hence the molecule is polar, CH3 bond dipole on each side, causing distinct positive and negative regions in the molecule. However, in case of a trans but2-ene molecule, the two CH3 groups are present on the opposite sides of the double bond. Thus, the bond dipoles of each CH3 bond cancel each other, making the molecule non-polar. Hence, we can conclude that trans isomers are more stable than cis isomers. Alkenes can be prepared from alkynes, alkyl halides, bisenyl dihalides, and alcohols. Let's look at each of them in detail. To obtain alkenes from alkynes, we carry out partial catalytic hydrogenation. During this reaction, addition of a hydrogen molecule, that is, addition of two hydrogen atoms, takes place across the triple bond of the alkyne. There are two catalysts that are commonly used. One is palladized charcoal, which is partially deactivated using compounds like barium sulfate or quinoline. It is also known as Lindlar's catalyst. The other catalyst is sodium in liquid ammonia. For example, ethine, on reduction with palladized charcoal or sodium in liquid ammonia, forms ethane. Similarly, propine, on reduction with palladized charcoal or sodium in liquid ammonia, forms propane. Depending upon the nature of the catalyst used, a higher alkyne can be reduced to cis or trans alkene. Lower alkynes, such as ethyne, and propyne and higher terminal alkynes do not yield cis-trans isomers upon hydrogenation. When the catalyst used is Lindlar's catalyst, the alkene obtained shows cis geometry. When the catalyst used is sodium in liquid ammonia, the alkene obtained shows trans geometry. For example, 2-butene on reduction with palladized charcoal in presence of quinoline forms cis-2-butene. However, 2-butene on reduction with sodium in the presence of liquid ammonia forms trans-2-butene. Alkenes can also be obtained from dehydrohalogenation of alkyl halides. When an alkyl halide is heated in presence of alcoholic potash, it gives an alkene and one molecule of halogen acid is eliminated in the reaction. The hydrogen atom for the halogen acid is obtained from the carbon atom adjacent to the carbon atom attached to the halogen atom. The carbon atom attached directly to halogen is called alpha carbon, whereas the adjacent carbon is called beta carbon. Hence, the reaction is known as beta elimination reaction. As hydrogen and halogen atoms are removed in the form of halogen acid from alkyl halide, the reaction is also known as dehydrohalogenation reaction. For example, 1-chloroethane on heating with alcoholic potassium hydroxide forms ethene. During this reaction, the hydrogen and halogen atoms on adjacent carbon atoms of 1-chloroethane are eliminated in the form of hydrochloric acid. In a dehydrohalogenation reaction, if there are two possible positions where the double bond can be formed, then the product obtained is governed by Cbse's rule. Cbse's rule states that elimination will predominantly proceed to the formation of olefin in which the double bond is highly substituted. In other words, the hydrogen atom will be removed from the carbon atom possessing lesser number of hydrogens. The rate of reaction depends on the nature of alkyl group and the halogen respectively. The rate increases from primary to tertiary alkyl halides as shown here. The rate is also affected by the halogen atom attached and is the highest for iodine and lowest for chlorine. Another way to obtain alkenes is by the dehalogenation of vicinal dihalides. In vicinal dihalides, the two halogen atoms are attached to two adjacent carbon atoms. When such dihalides are treated with zinc metal, the zinc atom removes the two halogen atoms, forming zinc halide, leaving behind an alkene in the process. This reaction is also called dehalogenation, as zinc removes two halogen atoms simultaneously. For example, when dibromoethane is treated with zinc, it forms ethene and zinc bromide. And when 1,2-dibromopropane is treated with zinc, it forms propene and zinc bromide. Alkenes can also be obtained from alcohol using acidic dehydration process. When heated with concentrated sulfuric acid, the OH group of the alcohol and one hydrogen atom from the adjacent carbon atom are eliminated in the form of a water molecule, forming an alkene. Hence, the reaction is said to be acidic dehydration of alcohol. An example of this would be the dehydration reaction of ethanol on heating with concentrated sulfuric acid to form ethene. During this reaction, the hydrogen atom and the hydroxyl group from adjacent carbon atom are eliminated in the form of water to form ethene. Dehydration takes place in 3 stages. First, the alcohol is protonated by the acid catalyst to form a protonated alcohol. Secondly, the protonated alcohol loses a water molecule to give a carbocation. Finally, the carbocation formed loses a hydrogen ion and forms a double bond. Cbse's rule also governs the dehydration of alcohols. For example, in the dehydration of 2-butanol, there are 2 possible positions for the double bond. However, 2-butene is more substituted than 1-butene. Hence, the more predominant product is 2-butene. Thus, we see that alkenes can be obtained by many different methods. Now let us look at the physical properties of alkenes. Alkenes are colorless hydrocarbons. Except for ethene, all the other alkenes are odorless as well. The first 3 members of alkene homologous series are gases, the 4th to 14th are liquids, and all members above 15th are solids. Being non-polar compounds, alkenes are insoluble in water, but soluble in non-polar solvents like benzene and petroleum ether. Alkenes are unsaturated hydrocarbons consisting of a sigma bond and a pi bond. The typical reactions of alkenes involve the breaking of the weak pi bond to form 2 sigma bonds. Such reactions are called addition reactions. These addition reactions are usually electrophilic in nature, as the pi electrons of carbon-carbon double bond are available to any species seeking electrons. Let us study the following reactions in alkenes. Addition of dihydrogen, addition of halogens, addition of halogen acid, addition of sulfuric acid, addition of water, oxidation, ozonolysis, polymerization. Let's start with addition of dihydrogen to alkene. Alkenes react with dihydrogen in the presence of catalysts like finely divided nickel, palladium, or platinum to form alkanes. Such addition reactions are always cis addition reactions. For example, ethene in the presence of finely divided nickel, palladium, or platinum yields ethane. Similarly, propene yields propane. Now let's look at the addition of halogen to an alkene. Alkenes react with halogens such as chlorine and bromine to form vicinal dihaloalkanes. However, they don't react with iodine under normal conditions. For the reactions with chlorine and bromine, the alkenes and the halogens are mixed together in an inert solvent like carbon tetrachloride. Ethene reacts with bromine to give 1,2-dibromoethane. This reaction proceeds via the formation of an intermediate called cyclic bromonium ion. During the addition reaction between ethene and bromine, the reddish-brown color of bromine gets decolorized due to the formation of dibromoethane. Hence, this reaction is used as a test for unsaturation. Let us now look at the addition of halogen acid. Alkenes react with halogen acids to form haloalkanes. In the reaction with alkenes, hydrogen iodide is more reactive than hydrogen bromide, which is more reactive than hydrogen chloride. In the case of symmetrical alkenes, only one product is formed. For example, ethene on reaction with hydrogen bromide gives bromoethane, or 2-butene with hydrogen bromide gives 2-bromobutane. However, in the case of unsymmetrical alkene, two products are formed. For example, propene reacts with hydrogen bromide to form 2-bromopropane and 1-bromopropane. Of these, 2-bromopropane is a major product. This is in accordance with Markovnikov's rule, which states that during the addition of an unsymmetrical reagent to an unsymmetrical alkene, the negative part of the addendum is added to that unsaturated carbon which possesses lesser number of hydrogen atoms. In the reaction between propene and hydrogen bromide provides the electrophile H+ that attacks the carbon-carbon double bond, leading to the formation of primary and secondary carbocations. The secondary carbocation, being more stable, is formed readily. This secondary carbocation is attacked by the bromide ion to form 2-bromopropane. Hence, 2-bromopropane is a major product. However, the addition of hydrogen bromide to unsymmetrical alkenes like propene in the presence of peroxide is on the contrary to Markovnikov's rule and is known as anti-Markovnikov's addition or peroxide effect or Kharash effect, as it was first observed by M.S. Kharash and F.R. Mayo in 1933 at the University of Chicago. The peroxide effect takes place via the free radical mechanism. In this reaction, initially benzoyl peroxide undergoes homolysis to form benzene free radical. This attacks hydrogen bromide and results in the generation of a bromine free radical. This bromine free radical further propagates the reaction by attacking the double bond in propene. Hence, propene undergoes homolytic cleavage to produce less stable primary and non-stable secondary free radicals as shown here. The secondary free radical attacks hydrogen bromide to form bromopropane, and the primary free radical attacks hydrogen bromide to form 2-bromopropane. Thus, 2-bromopropane is formed as the major product. Now let us move to the addition reactions of alkene with sulfuric acid and water respectively. Alkene Alkenes react with cold concentrated sulfuric acid in accordance with Markovnikov's rule to form alkyl hydrogen sulfates. For example, ethene and propene react with cold concentrated sulfuric acid and form ethyl hydrogen sulfate and propyl hydrogen sulfate respectively. Alkenes react with water in accordance with Markovnikov's rule. In the presence of concentrated acids like sulfuric acid, a water molecule adds to an alkene molecule across the double bond to form alcohol. For example, 2-methylpropene reacts with water in presence of concentrated sulfuric acid to form 2-methylpropan-2-ol. Let us now look at the oxidation reactions of alkenes. Alkenes, on reacting with cold dilute aqueous solution of potassium permanganate, which is also called Bayer's reagent, produce vicinal glycols, that is, 1,2-diols. For example, ethene, on reaction with Bayer's reagent, forms ethane 1,2-diol or ethylene glycol. As the purple color of potassium permanganate decolorizes with the formation of glycol, this reaction is used as a test for unsaturation. Depending on the nature of alkene and experimental conditions, alkenes react with oxidizing agents such as acidic potassium permanganate or acidic potassium dichromate to form ketones or acids. For example, 2-methylpropene, on reacting with acidic potassium permanganate, gives propan-2,1 or acetone. On the other hand, but-2-ene, on reacting with acidic potassium permanganate, gives ethanoic acid. Let us now look at the addition of ozone to an alkene, which is also called ozonolysis. Alkenes react with ozone to form ozonides, which, on further hydrolysis, in the presence of zinc, form either aldehydes or ketones or both. For example, in this reaction, the ozone molecule is added across the double bond in ethene to give ethene ozonide. This, on hydrolysis, forms formaldehyde or methanol. The oxidation of alkenes by ozone to form ozonides, followed by its decomposition with water, is termed as ozonolysis. This reaction is useful in locating the position of the double bond in an unsaturated molecule. Let us look at another example of ozonolysis reaction of propene. Here, first propene and ozone react to form propene ozonide. The propene ozonide, on further hydrolysis, in the presence of zinc, undergoes cleavage to form ethanol and methanol. The products formed helps us to determine the position of the double bond in propene as shown here. Let us move on to the last reaction, that is polymerization. Alkenes undergo addition polymerization reaction when heated under pressure in the presence of suitable catalysts. In this, a large number of molecules of the same species join together to form a giant molecule called a polymer. The simple compound which forms the polymers are called monomers. For example, ethene, when heated to 1000 degrees Celsius under 1000 atmospheric pressure, undergoes polymerization to form polythene. Aromatic hydrocarbons containing 2 or more fused rings are called polycyclic aromatic compounds or polynuclear aromatic hydrocarbons. Coal tar is the main source of polynuclear aromatic hydrocarbons. These hydrocarbons possesses either a linear or an angular structure. An example of a hydrocarbon with a linear structure is naphthalene or anthracene, and that of with an angular structure is phenanthrene and pyrene. These hydrocarbons are carcinogenic. That is, they cause cancer. Examples of polynuclear hydrocarbons that cause cancer are 1,2-benzanthracene, 3-methylchloranthrene, 1,2-benzpyrene, 9,10-dimethyl 1,2-benzanthracene, and 1,2,5,6-dibenzanthracene. There is no general method by which we can predict as to which polynuclear hydrocarbons will be carcinogenic. However, it is found that the number and position of certain groups such as methyl, hydroxide, cyanide, and methoxy in these compounds give rise to carcinogenic tendencies. These polynuclear aromatic hydrocarbons enter the environment due to the incomplete combustion of coal, petroleum, tobacco, etc. On entering the human body, these compounds undergo various biochemical reactions and damage DNA. This causes a sudden change in the DNA structure, leading to cancer. The elimination of carcinogens from the environment can reduce the incidence of cancer to a great extent.